This week, we're covering material in Chapter 4 during our short week, and I'm going to call this material Natural Cycles. We're going to talk about keeping time and how the natural cycles set up by our universe have helped us humans keep track of time throughout the ages, even before we had our phones to keep track of time for us. So why do we need to keep time anyway? Maybe this is a pretty simple, question, but there is a lot of answers. From an astronomer's perspective, keeping time allows us to record rates of change, a speed or velocity of expanding bodies or objects that are orbiting other stars or other planets. We want to think about the area that can be swept out by an orbit or an expansion of an object. And we also want to keep track of how objects change in position in the sky from night to night, year to year. And those in particular are things that our ancestors picked up on really well. And from a human perspective, keeping time, of course, allows us to keep track of regular time intervals useful for us to define the hours, months, days, years. And, for ancient people, keeping time allowed them to know when they need to be planting their crops, when nearby rivers were going to be flooding, and so on. So to help us keep track of time, there are a few key points that we're going to talk about here. We call a line in the sky that goes from north overhead to south through zenith. We call that line the meridian. So here we have our celestial sphere. There's you in the middle, and we have north and south here. So the meridian is the line that goes directly from north all the way through zenith to south. That's what we call the meridian. And when the sun crosses the meridian in the daytime, this is when we call it noon. So when the sun passes our meridian, that's noon. And from one noon to the next noon, we call that a solar day, or sometimes it's called a synodic day. Now, not all solar days are equal. So us astronomers invented what we call the mean solar day, which is the 24 hours long when we think about the duration of one day. So that's our mean solar day that we define just to help us, know when it's 8 o'clock in the morning, when it's 10 o'clock at night. The fact that the solar day, the time it takes the sun to cross from the meridian to meridian each day, the fact that that synodic or solar day is not exactly 24 hours has to do with the fact that our Earth isn't spinning upright. It's tilted on its axis and it's spinning around that. And also our Earth has an elliptical orbit. That means that at some points during its orbit around the sun, it's going to be closer to the sun, and at some points it's going to be further away from the sun. And so that means that every synodic day or solar day, the time the sun passes the meridian at noon from day to day, isn't always going to be exactly the same length of time. We can also keep time by tracking motions of the stars. The motion of the stars and the motion of the sun aren't exactly the same, and you've probably figured that out by now, and maybe you've also experienced it inside the planetarium or playing around with stellarium. So we defined the synodic day or the solar day earlier by the time it takes the sun to cross from the meridian to meridian each day, okay? And then a day according to when a star, a very distant star that's not the sun, crosses the meridian is what we call a sidereal day. So sidereal day means that we're tracking how long it takes the star, very distant background star, to cross the meridian. A sidereal day is about 4 minutes shorter than a solar day. So remember, sidereal day was the time it takes the star to cross the meridian consecutively. So why is there this difference in time between the sidereal day and the solar day? Well, it has to do with two things. It has to do with the fact that every day we're progressing forward in our orbit around the sun, and also because every day we are spinning on our axis. So here we're looking at a top-down view of our solar system. We've got the sun here and the Earth here. So as the Earth moves in its orbit around the sun, it's moving about 1 degree per day around the orbit. So we've got 360 degrees in a circle. We've got about 365 days in a year. So we're moving forward a little bit off from about 1 degree per day. And during that 1 degree, as we move forward, our Earth is also spinning, okay? And so that rotation of the Earth and the fact that we're moving forward just a little bit every day along this orbit means that not every day will the sun be in exactly the same spot relative to the background stars when they cross the meridian. And so that's the reason why we have this offsets, because of the rotation of our Earth and the fact that every day we're moving forward approximately 1 degree on our axis. So the position of things change a little bit in our sky. The part of keeping time is also understanding seasons. So let's talk about the reasons for the season on our planet. It all has to do with the tilt of our Earth on its axis. So we've already talked a lot about this, especially in the planetarium, but our Earth is tilted with respect to upright. It's tilted at an angle of 23.5 degrees, and our Earth spins around that axis, even though it's tilted, okay? And so this rotation axis of the Earth at 23.5 degrees with respect to upright is maintained from year to year, okay? So that 23.5 degree tilt is also maintained in the same direction relative to the background stars from year to year. Here is an example of what's happening in our solar system in order to give us seasons. Here's the sun. Over here in June, what we call the summer solstice, the beginning of summer, we have the Earth right here with its axis pointed toward the sun, okay? That means that our northern hemisphere is going to be more strongly or more efficiently heated by the sun's rays, the sun's light, the sun's energy, and that warms up our planet in the northern hemisphere in June. Okay, so while we're having summer in the northern hemisphere in June, actually the southern hemisphere is having their winter, because while our northern hemisphere is tilted more strongly toward the sun in June, the southern hemisphere is tilted away from the sun in June, okay? Now we're over here in September to what we call the autumnal equinox, or the beginning of fall, okay? Around September 21st. And then we come over here to 180 degrees on the other side of our orbit around the sun to December. And in December, we see the tilt of our planet. Here, the northern hemisphere is tilted away from the sun, okay? And then when the northern hemisphere is tilted away from the sun in December, that's when we have northern hemisphere winter. But the southern hemisphere, you see, is more strongly tilted toward the sun in December. And so in December, when the northern hemisphere is having their winter, the southern hemisphere is having their summer. So the northern and southern hemisphere alternate receiving on a yearly cycle the majority of the direct light from the sun. And this leads to us having seasons on our planet. If you had a stronger tilt of the planet, you would have a stronger variation in seasons. If you had a smaller tilt of your planet, you'd have a weaker variation in the seasons. It's a common misconception that seasons occur because the Earth orbits the sun in an ellipse. That's not the reason for it being hot in the summertime and cold in the wintertime. And again, it's all about the tilt. The Sun-Earth distance does change because our Earth is not orbiting the sun in a perfect circle. It orbits in sort of this elongated, stretched kind of football shape like you see here. The Sun-Earth distance only changes by about 3% during the course of the entire year. So It's not our variation of our distance away from the sun that causes the seasons. It really is the tilt. So let me show you here what we're talking about. So here I have the sun, and here is our Earth's orbit around the sun, a very exaggerated ellipse. It's not this elliptical, this is just exaggerated. The orbit is stretched out just for effect. So here we are in January at what we call the periapsis. The periapsis is the closest point in an orbit to your central star. So when periapsis happens, we're in January. So in January, we're actually closer to the sun than we are at any other time. So in January, our northern hemisphere winter time, we are actually closer to the sun at a distance of about 147 million kilometers. Let me come over here to March, June, and then what we call apoapsis is the furthest distance that we are away from the sun. And that furthest distance occurs not in wintertime, but it occurs when we're having our northern hemisphere summer. So in the northern hemisphere, we're actually further away from the sun in the summertime than we are in the wintertime. And so in July at apoapsis, our furthest distance away from the sun, we are at a distance of 152 million kilometers. So there's just a few million kilometers difference between January, when we have our closest approach to the sun, and July, when we have our furthest distance away from the sun. Let's talk a little bit more about why it feels warm in the summer and cold in the winter. It all has to do with the intensity of the sunlight striking the ground, and that also depends on the sun's angle in the sky. So when the sun is at a lower angle in our sky, the same amount of energy from the sun is spread out over a larger area of the ground, and so our ground is heated less efficiently. Okay, so here we have an example. We've got our Earth tilted such that the sun is over here, and our tilt of our planet is tilting towards the sun such that we're having northern hemisphere summer and southern hemisphere winter. Okay, so imagine that beam of light striking the surface of the Earth. That beam of light in the northern hemisphere is going to be oriented more closely to the vertical, more closely to straight up, okay? And so that beam of light is going to be more strongly focused and cover a smaller amount of area, okay? And then, so that's going to heat up the planet more efficiently in the northern hemisphere. At this same time, we have the southern hemisphere experiencing their winter because that light from the sun is more inclined with respect to the vertical. In the wintertime, the sun is going to appear lower in the sky, and so the rays of light coming from the sun are going to be hitting our planet not vertically as much as they do in the summertime, but at more of an angle as they do in the wintertime. And so that same amount of energy striking the planet ends up being spread out over a larger area because of that angle that energy is striking the surface of our planet with. So you've got the same amount of energy spread out over a larger area in the wintertime, and that doesn't heat up the planet as efficiently. And so that's the reason why we feel warm in the summer and cold in the winter. Other planets in our solar system are tilted with respect to their axis. Saturn's axis is tilted by 27 degrees, so even more strongly tilted than our planet. It also takes Saturn 29 years to make one complete orbit around the sun. So if we were to describe the length of Saturn's seasons, those seasons, Saturn would still experience summer, winter, fall, and autumn. But instead of being spread out over 365 days like they are for us, they're spread out over 29 years for Saturn. So if we say 29 is almost 30 years and divide that by 4, that means that each season on Saturn is about 7.5 years because it takes that planet 30 years to orbit around the sun once. And it has a substantial tilt. So that planet is also going to be experiencing seasons even more intensely than we do here on our planet. Jupiter's axis is only tilted by about 3 degrees. And so I'm going to ask you to think about how the seasons on Earth would be different if we were only tilted by 3 degrees like Jupiter.